my mom was like, that's so stop doing that.
So just as a heads up, okay, not sure if we've been paying attention to the sequence or the schedule for this unit, that table at the beginning of your notes. We are getting towards the end. We're going to finish this little free response question today and then start the last section of this unit. Okay, so fairly short unit because we've only had 4 sections to go over. So that means that next week we're going to be having a partner quiz and a unit test. So my game plan is to, this last section that we're going to start today, we're going to keep working through it the rest of this week. On Monday, we're going to have our free response kind of review practice day, which means Tuesday will be your partner quiz. Wednesday, you'll have as another review day for the unit test, and the unit test will be on Thursday and Friday. Okay, so that means the homework for the unit will be due on Thursday next week, giving you kind of a week notice. Okay, so since we're going to get the test in by Friday, which is when the quarter ends, it will be the last assignment on this quarter. So I think some of you were hoping that that would happen because you might be borderline or want to improve a little bit for the quarter. So we're going to be able to get that in. Okay? Just as a heads up. So next week we have partner quiz and unit test going to happen. All right, so let's take a look at this free response question. You might see something like this next week because it's relating to the symmetry stuff we've been dealing with. In the table below, we have some ordered pairs or values from a function called f of x. And notice how they only go from 0 to 6, okay, on the x-axis. If you were to plot those points, you could connect them using line segments. So it's going to look kind of jagged when we go ahead and graph these points. We're not going to connect them using curves, okay, straight lines. So we're going to use this table to help us answer the rest of these questions in the free response set. So take a look at part A. Suppose that this notation is true. Okay? We kind of saw this yesterday in terms of our classifying even and odd functions. You really got to think about what does this notation mean? Okay, what is it telling you? And if you look at it really closely, the left-hand side is saying if you were to plug in negative x, because that's your input value, you would equal or get out f of x, which usually represents an original function. So can we think about from yesterday, if you plug in a negative x and you get out the original, what type of symmetry or classification are we talking about? Yeah. The y-axis symmetry. Okay, so we'll label this y-axis symmetry. Do we know what the classification is though, like the word we use? Instead of saying y-axis reflective symmetry, we can simply say blank. Yeah.
Even.
Even. Good. Okay, so with that concept, with that idea that we now know based off of that notation, we're going to sketch the graph of f of x on the interval from -6 to +6. So we're going to fill up this entire graph. But the issue is the points they give us only go from 0 to 6. So these points are going to fill up half the graph. We should be able to fill up the other half with this idea. So let's see if we can do that. Let's go ahead and plot the points that they give us for f of x. And we're going to connect them using line segments. Okay, connect the dots. So Rebecca said that we should anticipate y-axis symmetry because we have an even function. So if we were to take this graph based off the points they give us and fold them over the y-axis, we should be able to fill in the other half of the graph that we don't know but that they want us to plot, because notice how it goes from -6. We should have something over here. Okay, so how might you describe the folding idea. Okay, how can we determine where these points would land on the other side? Can we visualize that? Okay, if you were to take this point and fold it over the y-axis, it would land there. This point folded over would be there. And if we do some other folding, we'd be there. The origin point, though, really isn't moving because the origin is on the y-axis. That's where the crease happens. So that point is kind of landing on itself when you try to fold it over. Does that look like a y-axis symmetric graph? Right? You'd be able to fold it here and the blue and red would match up. Okay, so they do want us to kind of explain our reasoning. How did you know you were able to plot this left-handed side? You're going to have to write some type of sentence, okay, some type of justification. So maybe we'll say, since f of negative x equaled f of x, okay, that notation they told us at the top, since they told us that, we know the graph should have y-axis symmetry. Okay, so that's what we used. That's what we applied to the graph to get the other half that we didn't know. So explain your reasoning, justify your work. You're going to have some type of sentence or two, just as an explanation. Are we doing okay with that? Does that make sense? All right, we're going to step it up a little bit with the next one. Sketch a graph of y equals the opposite of f of x plus 2 on the interval from -6 to +6. So again, we're going to have to fill up the whole graph. Show or explain how you got the new coordinates that make up that graph, which has the same characteristics as the function in part A. So if we look at what we did in part A, didn't we say that graph had y-axis symmetry? Okay, it was even. So we might have to use that concept again to help us with this graph. Okay, the same characteristics, that same idea that we discovered in part A. All right, so let's take a look at this one. We're going to sketch a graph of this y equation, but notice how it involves the f of x points. It says that function notation. But it's not just the f of x points. We want the opposite of the f of x point and then adding 2. Notice how those are transformations. You are changing the values somehow. So can we describe the transformations based off of the way that equation looks? Can you identify any movement? Yeah.
Maybe up to.
Up to, okay. Mara, did you have another one, or was that what you were going to say?
I have a question.
Sure.
What does
Even, oh, you weren't here yesterday.
Yeah, it's all those.
Oh, that's right. Okay. So we were talking about 4 different types of symmetry. We had the origin, which is the rotating one, and then you had the 3 folding ones, the y-axis, the x-axis, and then the diagonal one from the other day. We focused on 2 of those specifically yesterday. The y-axis is referred to as an even function, just a different way of classifying it. And then the origin, the rotational one, is called odd. It's just another way to describe the type of symmetry. So when I say y-axis symmetry, even is the same idea. They're kind of synonymous with each other. Okay? Does that help a little bit? Okay. Anything else going on in that equation as far as transformations? So the plus 2 is up to. What about the negative out front? I hope we haven't lost it yet. Negative on outside versus negative on inside. How does that change a graph? do you think, Grant?
It'll reflect on the x-axis.
Good. Okay, so x-axis reflection or flip. Good. Okay, so if those are the transformations we can identify, they want us to explain or show where the new coordinates are coming from. So using these transformations, what would happen to the coordinates? If you're moving a point up to, are you changing an x value or a y value? Yeah.
Be y, so y plus 2.
Y plus 2, perfect, okay. And then if you're flipping a point over the x-axis, are you changing an x value or a y value? Yeah. It's actually changing the y value, and we would make the y value negative. So it's the flips are the hardest ones to imagine. If you pick a point and fold it over the x-axis, notice how the x location stays the same, but the y location changes. So the y is actually negative. So if those are the only two transformations and they both are affecting the y coordinate, that means the x coordinate is staying the same. Okay, there's no effect or change for that number. All right, so let's go ahead and graph the points that we are able to. We're going to take the f of x points from the top and apply these transformations, and we're going to see where they land on that right-hand side. So this first point of 0, 0, if you were to plug 0 in for x, it would stay a 0. But if you were to plug in the 0 for y, you would get 2. So this is kind of the beginning point, and after you transform it, this is where it would be. So we'll plot that point. We're going to go through all the other ones. So the next ordered pair is 1, 2. If you substitute 1 in for x, that's not going to change. But if you plug in 2 for y, it's now 0. So after you transform that original point, it's now located on the x-axis. So if we keep going through the points, we'll get 2, 0, 4, negative 3, and looks like 6, negative 3. Again, connecting them in straight lines. There's our transformed graph. All right, so that only gives us half of the graph though. Okay, they wanted us to graph it on the interval from -6 to +6. So how might we fill in this left half that we're not really sure of just yet? Is there something else we can take into consideration? Something else we kind of labeled but haven't really used yet? Maybe think about how we did the last one. We had half the graph. What can we do? Yeah.
Well, since it's even, it would be over the x-axis still.
Y-axis.
Oh, sorry.
That's okay. So we know that this graph should have the same characteristics as the one before. Okay, it has that even property to it, the y-axis symmetry. So we're going to take these points that we plotted and fold them over the y-axis to get, or the left, or to see what the left-handed side of this graph would look like. And notice how that one kind of makes sense because we can fold it across the y-axis and the blue and red graph would match up. Okay, so this one was very similar to part A. We just had this extra transformation piece to take into account. So hopefully we haven't lost that just yet, or ever for that matter. Okay, let's try the last one. Suppose that we had this notation. Okay, we got to think about what that's telling us or representing. So if we were to substitute in a negative x, we would get out the opposite of an original equation, or f of x. what's that signifying? Can we classify the symmetry or describe by name the type of function we have? For those of us that were here yesterday? Yeah.
Odd.
Okay, so when we plug in, notice how this is kind of similar. When you plug in negative x, you get out the original. Okay, that's signifying an even graph or y-axis symmetry. However, if you plug in negative x and you get out the opposite of the original, that's what's classifying our function as odd. And this is the origin symmetry. So with this concept, again, we're going to try to sketch the graph on the entire grid that's given to us. And we're going to plot the points of f of x. So again, plot the points from the top. Yeah, just pick a seat. Or did you have to go somewhere else? You're good? Just pick a seat. Okay. All right, so this is what the original points look like from the function. We want to figure out what the left-handed side looks like, and we're going to use the idea that we have this origin symmetry to help us out. So this might be a little difficult to analyze, or visualize rather, but if you were to take this graph and rotate it 180 degrees, we have to figure out where it would land on this left-hand side. Can you kind of maybe describe where some of these points might land? Can we visualize that? For instance, if you were to rotate this point 180 degrees, what do you think? Right there? Not quite. Okay, it's called... I like that one better. Okay, it's called origin symmetry. Okay, take a look at this. If you were to trace this point through the origin to the other side, that's where it would land. Can you see that? Origin symmetry, if you rotate it, you're going to go through the origin. If we do the same thing for the other point, through the origin to the other side, looks like we'd land there. Maybe you're starting to see some patterns. Okay, I think we've talked about patterns with the ordered pairs. If the original point is at 2, 2, the symmetric point is at -2, -2. Okay, both x and y values become opposite. So the next point we had was 4, 5, which means the symmetric point for origin symmetry would be -4, -5. And very similarly, the last one we'd have -6, -5. So connecting those dots, we'd have the left-handed side. Okay. If you wanted to give it a shot, maybe flip your paper upside down. You should have the same graph. Okay, just to double check your work, it should look exactly the same as it does right side up. All right. So it says explain your reasoning. We're going to have to write another little sentence here. Probably very similar to the one we wrote for part A. Since f of -x equals -f of x, we know the graph should have origin symmetry. Are we okay with that free response? I know the notation's a little tricky, but after you figure out what it means, do you think you'd be able to go through some of those problems? Good. All right. So that's the end of like even and odd stuff. Okay, even y-axis symmetry, odd origin symmetry. Basic idea there. What we're going to do in our last section is take a look at another type of special symmetry we discussed. So we had 4 of them. We had origin symmetry, y-axis symmetry, x-axis symmetry, and then that diagonal symmetry. So the y-axis and origin were even and odd classifications. We're going to take a look at that diagonal symmetry a little bit further in this section. Okay? So in order to get there, though, we're going to have to talk about a few vocabulary terms first, just so we can kind of build our mathematical vocabulary or understanding. What is your idea of a function or basic knowledge of a function at this point? We worked a lot with functions at the beginning of year, like inputs and outputs. What did we say a function was, or what do you know a function to be? How would you describe it? Either graphically or in terms of an equation, anything. Yeah?
If you put something in and something else come out.
You plug something in, you get something out. I like it. How many items, or when you plug something in, how many items do you get out? One. You plug one thing in, you get one thing out. Okay, so that is the basic idea. So we're going to say a function is a relationship or connection between x and y such that each x value has only one y value. You plug one x in and you only get one y value out. Okay, so in terms of points on a graph, let's say the point 2, -3 is on a graph, then there should be no other point that has which one of those values. Can we have another point that has the same x value, or can we have another point that has the same y value? You kind of got to think about a graph. If you plug one number in, you only get one number out. What do you think, Grant? The x's can't repeat. Okay, so you can have no other point that has an x value of 2. Okay, so the x's cannot repeat. You can have repeating y's in order for it to be a function. For instance, if you had 2, -3, and 5, -3, that's okay because it satisfies this definition. You plug in 2, you only get out 3. You plug in 5, you only get out -3. Okay, you would not be able to have 2, 0, for instance, because notice how if you plug in 2, this is saying you can get out either -3 or 0. That's not a function because we have 2 possible y values, not just 1. So the big idea of a function is that there's no repeating x values. One thing in, one thing out. What we're going to describe in this section is something called a one-to-one function. Okay, and it's very, very similar to the definition of a function. It's just that we're switching the ideas of the x and y relationship. So for instance, a one-to-one function, we'll say, is a relationship between x and y such that each y value this time has only one x value. Do you see how that's basically the same definition? We're just switching the concept of the variables. So each y value has only one x value. Okay, so in order for a graph or an equation to be a function, you can have no repeating x's. What do you think the condition is for a one-to-one function? No repeating Yeah.
Whys.
No repeating y's. Okay, so it's the same idea. We're just switching the way in which the variables are used or represented. Okay, so let's take a look at different ways we can determine if a function is one-to-one depending on the information provided for us. Okay, numerically means we're looking at like a table of values or those ordered pairs. Graphically, you know that's a picture. Analytically, that usually means we have some type of an equation to analyze. Okay, so numerically are numbers from a table, graphical is a picture, analytical, that by hand idea, is when you have an equation. So let's think about this. We just said in terms of a table, in order for a graph to be one-to-one, there should be no repeating y's. So we'll say a function is one-to-one if there are no repeating y values in a table. All right, what if we had a graph? Okay, think about back to algebra. How did you determine graphically if a graph was a function? If you had a picture, what did you do to determine if you plugged in one x, you only got out one y? It was some type of test. That gives you a clue. Yeah. Vertical line test. Okay, so to determine if a graph is a function, you use a vertical line test. What do you think we're going to use to determine if a graph is a one-to-one function? Instead of a vertical line, we're going to use a horizontal. Okay, so the whole idea again between function and one-to-one function is switching that x and y idea. So instead of using a vertical line for a function, we're going to use a horizontal line to determine one-to-one. Okay, so graphically, a function is one-to-one if the graph passes the, we'll say, horizontal line test, HLT for short. So just like the vertical line test, you're testing to see if it only touches once. We're going to apply that same idea, but to a horizontal line. We want to see if it only touches once. Does that make sense? All right. An equation can be the tricky one because I think the table and graphical ones are the easiest ones to kind of pick apart. Equations get difficult because you don't have a visual example. You just have that equation to work off of. But we've done a lot of analyzing this year in terms of equations and graphs. For instance, if I gave you a linear function, okay, a linear equation, do you know what that graph would look like? Could you describe the shape? What would a linear graph be? What would it look like? Linear, aka? Yeah?
It's just a straight line.
It's just a straight line. It might have some slope to it. Yeah, straight line. What if I gave you an absolute value equation? What would that graph look like? Yeah. A V. Okay, so if you're given an equation, you kind of have to think about what would the graph look like. And if you can determine what the graph looks like, couldn't you apply that horizontal line test to it to confirm if it's one-to-one or not? So the equations are a little tricky. You're going to have to recognize the shape of the graph. We'll say based off of the equation. So if you can recognize the shape of the graph, you can then use that horizontal line test to determine if it's one-to-one or not. Okay, so we reviewed a function. We have a new vocab word, okay, one-to-one function. Notice how it's a very similar idea, just switching the variables or concepts from a regular function. we're going to talk about a new vocab word too at the bottom. Okay, the inverse of a function is defined to be an equation formed by switching. Do you know what? Instead of equation, let's write function. Sorry. A function formed by switching the domain and range values. When I say domain, which variable am I talking about? X, good, and range would then therefore be Y. Okay, so here is again that concept of switching. Okay, to find an inverse, we're going to switch the domain and range, aka we're going to switch the X and the Y. Okay, so we've seen this idea of switching X's and Y's previously in some of the other things we wrote down. So, inverse, switching variables, 1 to 1, okay? Each Y value has only one X value, two new terms for us. So we're going to focus a lot on this idea of an inverse in this section, and we got to use the vocab word of 1 to 1 in some instances to help us determine if an inverse exists. Okay, are you able to switch the domain and range values? So we're going to investigate this idea a little bit further. What property of a function must exist in order for the inverse to exist as well, in order for you to be able to switch the domain and range values? Okay, we're going to talk about why. So let me ask you this. If f of x, some equation or graph, is not 1 to 1, what does that mean is happening? If you're not 1 to 1. What do you think, Addison? You have multiple points at the same y value, so you have repeating y's. Okay, let's write that down. If f of x is not 1 to 1, then there are repeating y values. All right, so if we're not 1 to 1, we know we have repeating y's. If you were to apply an inverse to this function, if you were to switch the x's and y's, these repeating y's would then become what? If you were to switch the domain and range, if you were to switch the x's and y's, these repeating y's in the original function would become what in the inverse? Yeah. They would become repeating x's, right? Okay, so let's write that down. So, if the inverse is applied, these repeating y's are now repeating x's. Does that make sense? Inverse means switch domain and range, switch x's and y's. So let's see where this is leading us. Okay, so we applied the inverse. If the inverse now has repeating x's, is the inverse a function? We're shaking our heads no. That's good, because our definition of a function from the very top is what you plug in 1x, you get out 1y, aka there's no repeating x's. Okay, so we can say this means the inverse is not a function. because it has those repeating x's. Okay. So back to the original question. What property of a function must exist in order for a function, or in order for the inverse to be a function? Okay, in order for the inverse to exist. All of this connective ideas here. Do you see it, Mario? Yeah. Okay, the original function, f of x, has to be 1 to 1. Because notice how we kind of explored here, what if it wasn't? So if an original function wasn't 1 to 1, that means the inverse is not a function. So in order for the inverse to be a function, the original equation has to be 1 to 1. Does that make sense? If something's not something, then it has to be something else in order for it to kind of work out. So we'll say, therefore, f of x must be 1 to 1 in order for the, I'm going to run out of room, in order for the, I'm going to write it down here, inverse to exist. I wrote it a little big. All right, so we have a stipulation here. In order for us to be able to switch the x and y values, in order to switch the domain and range, okay, the original function, f of x, must be 1 to 1, which means it doesn't have any repeating y's, which means it passes that horizontal line test, okay, in terms of a graph. So we're going to investigate that idea a little bit further. I hope that makes sense, what we wrote down there. Okay, so an original function has to be 1 to 1 in order for the inverse to exist. So let's take a look at what's on the back here. Okay, so now that we know a function must be 1 to 1 in order for an inverse to exist, we're going to go ahead and try to determine, again, numerically, graphically, and analytically, how we can determine if the inverse is a function. No repeating x's, right? Okay, so numerically, based off of a table, maybe we have a table of values for an original function. If we wanted to apply an inverse, we would have to switch the x and y values in the table, right? Okay, the whole idea of an inverse is about switching x's and y's. So maybe we'll say in a table, we need to switch the x and y values to create the inverse table. Okay, switching domain and range, switching x's and y's. What if we wanted to try to graph an inverse? Okay, this time we're going to make a picture. Maybe we can use the numerical or table example to help us with that. Isn't it true if you have a graph, can't you write down the ordered pairs from the graph? And therefore the ordered pairs can be made into a table. Do you see how those two are kind of connected to each other? Okay, so we're going to make a table from the graph of f of x, okay, the original equation, and switch the x and y coordinates, okay, the domain and range values, for the inverse graph. We're writing these down now. We're eventually going to apply them. We have a lot of examples to go over, but I just want to make sure you have these kind of in your notes. Okay. Analytically means we have some type of an equation to look at. Okay. Okay, so in an equation, remember the whole idea of an inverse is switching the x's and y's. So in the equation, let's go ahead and switch the x and y values. But if we switch the x's and y's, okay, the equation might look a little weird, just giving you a little heads up. So then what we're going to do is solve for the y variable, because we're used to seeing a y equals equation, right? We're not used to seeing an x equals. So when we switch the variables, it's going to look like x equals. We're going to change it back into y equals. Okay. Now there's a specific notation we use to mean the inverse, and that kind of shows up in the paragraph underneath these boxes. Do you guys see that f to the little -1 power? Have we seen that before, perhaps? Previously in another math class? Some say yes, some say no. That's completely okay. This notation is very specific, okay? It's signifying this inverse idea that you switch the x's and y's. So when we get done solving for y, we're going to rewrite the equation just using f of the -1 symbol. Okay, and when we get to examples, we'll work with that. Okay, but that notation means inverse, that you switch the x's and y's. Okay, so now that we have those, we're going to reference them as we go through these different examples. So take a look at some of the ones that we're going to tackle here. For each of the following functions, determine if the inverse exists. Okay, is f of x 1-to-1? We're going to have to check that out. If it does, then find the inverse. Okay, go through the process of switching those x's and y's, those domains and ranges. If a relation is given numerically, okay, that's in a table format, give the table of the inverse. If a relation is given as a graph, make a sketch of the inverse. If a relation is an analytical form, okay, an equation, find the equation of the inverse. Okay, so if we can prove that the inverse exists, we're going to actually go ahead and find it, whether that means through a table, a graph, or an equation. So we're going to see how all three of these work. All right, so let's take a look at a table first. In order to determine if an inverse exists, we have to first check, is the original function 1-to-1? So take a look at the table of this original function f of x. Can you determine if it's 1-to-1 or not? 1-to-1 or not? What are you looking for? What are you trying to analyze? You might have to go back to our definition of 1-to-1. Let's approach it this way. Is this table of values here representing a function? If you were to plug in one number, would you only ever get out one number? You plug in 5, you get out 2, right? We'll check that out tomorrow, okay? Bunch of example times tomorrow. That bell rang a little sooner than I thought it was going to.